In this video cast, we'll take a look at how K can be calculated using various data from various reactions to find the equilibrium constant. Question number 2. For the Haber process, N2 plus 3H2 goes to 2NH3. This is the production of ammonia. K sub P is equal to 1.45 times 10 to the negative fifth at 500 degrees Celsius. Notice it's a number smaller than 1, which means the reactants are favored. In an equilibrium mixture of the three gases at 500 degrees Celsius, the partial pressure of H2 is, and that of N2 is, what is the partial pressure of NH3 in this equilibrium mixture? First thing we need to do is write the equilibrium constant expression, which would be products NH3, and since it's in terms of pressures, we usually write it as PNH3 in parentheses, to the second power, divided by the pressure of nitrogen gas to the first power, times the pressure of hydrogen gas, in this case to the third power, because there's a 3 in front of it. This is the equilibrium constant that we sometimes call K sub P, or K with a small p below it, because it's written in terms of pressures. This is equal to the thing that we want to know, NH3 squared, we'll call that X, because that's the thing we want to know at equilibrium, divided by the pressure of nitrogen in equilibrium, and notice they tell us that right here. Nitrogen is 0.432 atmospheres times the pressure of hydrogen, which they tell us is 0.928 atmospheres. And notice this has to be to the third power. And this is equal to our K value, which in this case is 1.45 times 10 to the negative fifth. Times 10 to the negative fifth. So we need to take this equation now and solve it for x squared. Let's take and let's multiply both sides of this reaction by 0.432 and by 0.928 cubed. If we multiply this side of the reaction by the same thing, we'll get rid of these. And we end up with x squared equaling 1.45 times 10 to the negative fifth times 0.432 times 0.928 to the third power. And of course we want to find just regular x, so we're going to end up square rooting both sides to get x by itself. And if we do this, x turns out equaling 2.24 times 10 to the negative third. And we're looking for pressure, and notice our pressures are all given to us in atmospheres and atmospheres. So we're assuming in this case, since we're looking for pressure, we're going to end up with a pressure in atmospheres. So you can use the equilibrium constant expression like this if you know the equilibrium constant and you know a couple of the pressures or concentrations at equilibrium. You can solve for a third. Question number 3. A 1 liter flask filled with 1 mole of H2 and 2 moles of I2 at 448. The value of the equilibrium constant is 50.5 at that temperature. What are the equilibrium concentrations of H2, I2, and HI in moles per liter? Well, the first thing you need to do in a problem like this, where you're given some initial concentrations, 1 mole and 2 mole, and notice that it's in a 1 liter flask, so you just take moles and divide it by liters to get your molarity. So it's 1 molar in H2 and 2 molar in I2, is to write the equation H2 plus I2 goes to 2HI, and set up a table. Initial, change, equilibrium, and fill in what you know. We know that we start with 1 mole of H2, and we start with 2 moles or 2 molar of I2, and we start with none of this. It doesn't tell us any other information. It doesn't tell us the ending concentrations of H2, I2, or 2HI, or we could fill those in and then work backwards to figure out what the change is. And so, since we don't know those, we have to call the change that's going to occur the variable, or the unknown. When this happens, we'll lose H2, we will lose X amount of I2, and we will gain 2X of HI. So in the end, we'll end up with 1 minus X of H2, 2 minus X of I2, and 2X amount of HI, because 0 plus 2X is 2X. We can now take these ending values, put them into our equilibrium constant expression, since we know the equilibrium constant is 50.5, and solve for X. Toss it back into each one of these, and we'll know what our ending concentrations are for H2, I2, and HI. So the equilibrium constant expression for this, K sub C, would be products HI to the second power divided by H2 to the first power times I2 to the first power. And HI is equal to 2X, so we have to put 2X in here and then square it. H2, which is 1 minus X, times I2, which is 2 minus X. And those of you that are a bit math savvy are now cringing, because you'll notice what we have down here and what we have up here. We'll end up with 4X squared on the top, and here we have to do first, inner, outer, and last. FOIL, remember that deadly word. And it turns out that we get X squared minus 3X plus 2 when you FOIL this entire thing to get this. And this is all equal to our equilibrium constant, which they tell us up here is 50.5. So this expression is equal to 50.5, and you can now see that we need to take this critter, put it on the other side, and set the whole thing equal to 0. And if you have an equation solving calculator with the fancy equation solver, you can now solve for X using the quadratic formula. Or if you set this up and you don't have the quadratic formula, I'm going to move this up here. It turns out that this expands to look like 46.5x squared plus a negative 151.5x plus 101 is equal to 0. And now you can take this as your 3 terms to put into the quadratic formula solver if you have it on your calculator, or you can shove it into the quadratic equation yourself, which would be negative of a negative 151.5 plus or minus the square root of negative 151.5 squared minus 4AC all over 2A. And you can plug the numbers in, but probably better to get your equation solving calculator. And when you do that, you find out that X has 2 values, 2 possible values. One of them is 2.323, or the other one is 0.935. And you have to evaluate these two and decide which one makes sense. Which one makes sense. And if you plug these numbers back into the equation right here to find out what H would be equal to, I2 would be equal to, and HI would be equal to at the end, if you use 2.23, you'll notice that hydrogen ends up being 1 minus 2.23, and you'd end up with a negative concentration for H2, which is impossible. So you throw out this solution, and it turns out that you take 1 minus 0.935 for the hydrogen, and that turns out to be a concentration of 0.065. For the iodine, I2, you end up with 2 minus 0.935, which turns out to be 1.065. And for the HI, you end up with 2 times x, which is 2 times 0.935, which turns out to be 1.87 molar. These, folks, are the answers after all that wonderful math. Now, do all of them turn out like this? No, not at all. As a matter of fact, there hasn't been one where you have to apply the quadratic equation like this on an AP exam ever in the history of the AP exams. I believe there's one in your homework problems that you'll end up having to use the quadratic formula for, but usually they try to give you a way to get out of it where you can take the square root of something to remove it. I'm just going to set up the last one because it's very similar to number 3 and it ends up using the quadratic once again, but it's not necessary to do. So let's look at problem number 4, which is a plus 2b goes to d, and it gives you a k sub c, and initially a is 1.5, b is 0.5, and d is 1.0 molar. First thing to do here, remember, is to just set up your equation. A plus 2b goes to d, and write an ICE table, initial change equilibrium. Set up what you know to start with. A starts out with 1.5, b starts out with 0.5, and d ends up with 1. Your change then is to lose x, and gain x. Notice you'll lose 2x here because there's a 2 in front of the b. And you end up at the end with 1.5 minus x, b being 0.5 minus 2x, and d being 1 plus x. Now you can take this and plop it into the equilibrium constant expression, which is equal to 5 times 10 to the second. And this is equal to products divided by reactants. So d is your product, 1 plus x, divided by the reactants. A is 1.5 minus x, and b is 0.5 minus 2x. And don't forget that has to be to the second power because there's a 2 in front of the b. From here, you'd have to expand this animal and then eventually solve a quadratic equation looking for x once again. That's the kind of setup you can end up with, but like I said before, very rarely do you end up with ones that have a quadratic equation, but it's better to show the hard one on the sample problem than to end up doing one without having seen a quadratic one before. The last part of this video cast, we're going to take a look at the effect of conditions on the position of equilibrium and apply something called Le Chatelier's principle, because it's a way of remembering how a change will affect the position of equilibrium. Pretty much bottom line, Le Chatelier's principle says that if you stress a system, it will adjust to reduce the stress. And it adjusts in a predictable, normal way. Fortunately, Le Chatelier's principle is very qualitative. You don't have to calculate anything. You just have to say more will go to the right or more will go to the left, or more will go to the products or more will go to the reactants. Here are the possible changes that you'll encounter. First of all, an increase or a decrease in concentration. If you increase the concentration of something, that means it will shift the reaction to the opposite side, and the equilibrium constant will not change. If you decrease the concentration, it will shift to that side to replace the amount that's lost, and of course K sub C won't change with that either. How about if you increase or decrease the pressure? Well, if you increase the pressure, it'll shift to the side with the least moles of gas to reduce that pressurized stress, and you won't change K sub C or K sub P. If you decrease the pressure, it'll shift to the side with the most moles of the gas to reduce that stress as well, and you won't change K sub C once again. Now, one that's not on this table is what happens if you change the volume. Well, remember, pressure and volume are inversely related to each other. Remember the vice president. If one goes up, the other one goes down. Or I should say, if the president goes down, the vice president goes up. So if you increase the volume and hold everything else constant, what are you doing to the pressure? You're reducing the pressure, and so you look right here for a decrease in pressure. It's a tricky way to ask you if the pressure is changed. A tricky way to ask pressure is being reduced by saying volume is being increased. The opposite, of course, is true as well. Let's say the volume is being reduced and everything else is held constant. Well, what are you doing? Well, you're increasing the pressure then of the reaction, and it will shift to the side with the least moles of gas. So watch for that volume change, because that can be an increase and decrease in pressure. Last two, you can increase the temperature or decrease the temperature. If you increase it, it will shift in the endothermic direction. And the best way to do an increase or decrease in temperature is to use heat as a reactant or a product. And of course, you'll change K with an increase or decrease in temperature, because temperature changes what the equilibrium constant is. A decrease in temperature will shift to the exothermic direction. And lastly, on this table, even though it doesn't affect K, is the addition of a catalyst. Remember, a catalyst only speeds up a reaction. It gives it an alternate pathway and decreases the activation energy. It does not change what results, in other words, the equilibrium. So don't let that trick you. Catalyst does not change equilibrium. Let's look at a couple of just quick examples with this. This is actually on the LSHS video cast as well, but let's just look and ask what would happen if we change something in some particular reactions. We'll take a look at these reactions and let's just make some things up about them. Even though this isn't the question for it, let's look at these particular reactions. And let's say this reaction right here was all gases, okay? And let's start from the top, and let's say that we increase the concentration of CO2. Increase the concentration of CO2. If we do that for this first reaction, we'd think that we would shift the reaction to the right, and that would be a good prediction that we would create more products. Let's say that we would remove some CF4 from this reaction. We'd take away some of this reactant right here. Well, if we do that, we'd actually, in effect, be reducing the concentration of CF4. And so the system would adjust to reduce that stress by producing more CF4 and shifting to the left or shifting to the reactant side. That would be like a decrease in concentration that we talked about here. Okay, let's talk about pressure or volume. Let's pretend we're looking at reaction D right now. And let's say they're all gases once again. And in this case, what we do is we increase the pressure of the system. If we increase the pressure of the system, it said it shifts to the side with the least moles of gas. Notice we said all of these were gases. There's 1, 2. Notice there's a 1 in front of each of these, but they're not written. It's just assumed you know that. 2 moles of gas on this side of the reaction, and there's 1 mole of gas on this side of the reaction. Well, if you increase the pressure, remember, it shifts to the side with the least moles of gas, so it will shift over here. Okay, let's say that what we do is we increase the volume of the system. Using this same reaction now, we increase the volume. Remember the vice president? If you increase the volume, what happens to the pressure? Well, the pressure is reduced. If you reduce the pressure, remember what it says. If you reduce the pressure, it will shift to the side with the most moles of gas to reduce that stress. So it will shift to this side, to the right side, and we'd say that the reaction would adjust by shifting to the products. Lastly, let's take a look at what temperature would do. And let's just pick a different reaction on here. Let's pick this one right down here, since it gives us some thermodynamic data right here. Notice that this is what's called an exothermic reaction because it has a negative sign right here. I think the best way to deal with these increases or decreases in temperature is to take the enthalpy and write it as a reactant or a product. If it's an exothermic reaction, write heat as a product. Write heat as a product. And then treat it just like you would with concentration. Let's say that we increase the temperature of this system. If we increase the temperature, it's like we're adding heat to this side of the reaction. Because if you increase the temperature, you're increasing heat. Well, if you increase the concentration of heat, what do? Remember, it says if you increase the concentration of something, you shift to the opposite side. So if we increase the temperature, we would shift the reaction to the left and therefore cause more reactants to be formed. Well, conversely, what happens if we decrease the temperature? Well, once again, we made sure to put heat as a reactant or a product. In this case, it's a product because it has a negative value. It's exothermic. If you decrease the temperature, it's like, in effect, that you're removing some of this heat. You're removing some of this heat. What does it say if you decrease the concentration of something? Well, it shifts to that side of the reaction. And so the reaction would shift to the right, and therefore we would produce more products. There's a lot more about Le Chatelier's principle in the next video cast.